This is Physics 102A, Chapter 8 homework solutions, starting with number 35. Lawnmower blade accelerates 98 radians per second squared. From rest, we have a time of 2.5 seconds. And the question is asking, what's the angular velocity in radians per second and revolutions per minute? So we'll use this equation. Omega equals omega naught plus alpha t. Omega naught is 0. So multiply alpha times t and you get 245 radians per second. To convert to revolutions per minute, 245 radians per second, we multiply by 60 seconds over a minute. We multiply by 1 revolution over 2 pi radians to get rid of the radians, and we have 2340 revolutions per minute. Number 37 asks about the Earth's average angular acceleration over 4 billion years. So we're going to use this equation. Average acceleration is change in omega over t. The time is 4 billion years, so a quick estimate, 4 billion times, there are pi times 10 to the 7th seconds in a year roughly. So it gives us about 4 pi times 10 to the 16th seconds. Now we need the different omegas. So omega 1, remember that omega is 2 pi over period. So omega 1 is the angular velocity that the Earth has now, 2 pi over a day, and a day is 86,400 seconds. And so we get omega 1 of 7.272 times 10 to the negative 5 radians per second. The initial omega for 14 hours, so 2 pi over 14 hours, convert hours to seconds, and so we get 1.247 times 10 to the negative 4 radians per second. When we plug these numbers into the equation, we get average alpha is the difference in the omegas over t, and we get negative 4.13 times 10 to the negative 22 radians per second squared. Number 39 involves a dentist drill. Now there are two phases here. I've labeled them phase A and phase B. We need to separate it. We can't apply one kinematic equation to the two different phases because the kinematic equations they only apply when there's a constant acceleration. Phase A and phase B have two different accelerations. So we'll take phase A as when it's accelerating at 615 radians per second squared. Phase B has 0 acceleration. And so the number of turns or radians that the drill has gone through is going to be theta for phase A plus theta for phase B. So we're going to solve for each of those. Theta for phase A is omega t, which goes to 0 because omega naught is 0, plus 1/2 alpha t squared. And again, that's just the time for phase A. And you should get 1356.075 radians. In order to solve for theta of phase B, we're going to need to know what omega 1 is. Now, omega 1 is the final velocity at the end of phase A, and it's the constant velocity of phase B. So we'll find it by taking, for phase A, omega 1 equals omega naught, which is 0, plus alpha times time of A. So we get that the dentist drill, by the time it's done with phase A, by the time it's done accelerating, it's at a speed of 1291.5 radians per second. Now we apply that to phase B. The number of radians it's gone through in phase B is omega 1 times the time of B, 9686.25 radians. Now that we know theta A and theta B, we add them up. We get 11,042 radians. The question is asking how many total revolutions has it gone through. So 1757.4, but since the question is asking how many total revolutions, we can just say 1757 total revolutions. Question number 41. 9,000 RPM slows down to 5,000 RPM with a constant acceleration over 3.5 seconds. So first we need to convert those to radians per second. And I've already shown how to do that conversion. So here's what they are. Omega naught is about 942 radians per second. Omega 1 becomes about 523.6 radians per second. To find the angular acceleration, it's alpha equals the difference of the omegas over t, omega 1 minus omega 2. I'm sorry, omega 1 minus omega naught over t. And since it's slowing down, we end up with a negative number, negative 119.7 radians per second squared. Question B is asking, through how many turns has it gone? So we use theta equals omega naught t plus 1/2 alpha t squared. Plug in those values and we get 2565.6 radians or 408.3 revolutions. Question C asks, through what distance does a point on the edge turn during this time? And so we're looking for the arc length, actually. S equals r times theta. We solve for theta in question B, so it's 9.4 centimeters times theta. And we get 24,117 centimeters. I've converted that to meters, so 241.2 meters. Number 54, compute the Earth's rotational inertia. Assume it's a uniform solid ball. So for a uniform solid ball, we have I equals 2/5 mr squared. We look up the mass and the radius of the Earth and plug those numbers in, and we get I equals 9.72 times 10 to the 37th kilograms meters squared. Number 55 then asks, find the Earth's rotational kinetic energy. So kinetic energy equals 1/2 I omega squared. We already solved for I in problem 54. Omega, we solved for this in a previous problem. Omega is 2 pi over 1 day, which is a period of 1 day, which is 86,400 seconds. And so when we plug in those values, we get a kinetic energy for the Earth of 2.57 times 10 to the 29th joules. Number 57. The power saw has kinetic energy 44 joules. Rotation rate drops to 1/2. What's its new kinetic energy? We're going to do this in an algebraic fashion, so without really caring what the moment of inertia is. We're going to bypass having to solve for that. Here's what we have. K naught, initial kinetic energy, is 44 joules. Omega 1 is 1/2 of omega naught. And we want to know what is K1. So we can start with K1 is 1/2 I omega 1 squared. Now we plug in this value for omega 1. So we have 1/2 I times 1/2 omega naught squared. When we distribute that squaring on the parentheses, the 1/2 inside the parentheses becomes 1/4, and I've put it out to the side here. So now we have kinetic energy 1 is 1/4 of 1/2 I omega naught squared. Now this 1/2 I omega naught squared, that's what the original kinetic energy was. So it becomes 1/4, excuse me, 1/4 times the original kinetic energy. 1/4 times 44 joules becomes 11 joules. Number 75. An auto mechanic applies a 65 Newton force near the end of a 35 centimeter long wrench. What's the maximum torque? Torque will be maximized when the mechanic is pushing at a perpendicular angle, when basically when the angle is 90 degrees, and so sine of the angle becomes 1. So torque equals force times lever arm times the sine of 90 degrees, 65 newtons times 0.35 meters, and that becomes 23 newton meters. Number 79. Two children sit at opposite ends of a 3.4 meter long seesaw with the fulcrum at its midpoint. Okay, that means that each child is 1.7 meters from the fulcrum. With the seesaw horizontal, find the net torque on the seesaw and its angular acceleration. Okay, so you see the diagram I have here. The first child, with the mass of 35 kilograms, he's applying a force of m1g, his weight. The second child is applying a force of m2g, which is his weight. As I've drawn the picture, and you might draw the picture slightly different. It might be backwards from mine, in which case, depending on how you set it up, how you draw the picture, you might get a positive or negative answer, but the absolute value of the net torque should come out the same. So as I've drawn the picture, the net torque is F1R1 minus F2R2. And the reason one is being added and the other is being subtracted is I want you to remember the convention that I introduced in class, which actually you learned in trigonometry class, which is that counterclockwise, we're going to call that the positive direction. Clockwise, we'll call that the negative direction. So child number 1 is pushing with a positive torque. Child number 2 is pushing clockwise with a negative torque. The sum of the torques then is m1g_r1 minus m2g_r2. You notice I've dropped the subscripts on the r's because both children are 1.7 meters away, so I just left it at r. I can factor out the g and the r. The sum of the torques is then gr times the difference of their masses. And I get negative 83.3 newtons meters. And I've just left my final answer as the absolute value of that because the negative just shows that according to the picture as I've drawn it, it's in the counterclockwise. It's negative, so it's in the clockwise direction. It basically goes in the way that makes the heavier child number 2, apply a greater torque. So 83.3 newton meters. Part B to the problem. Number 79, Part B says, what's the angular acceleration? Torque equals I times alpha, which means alpha, what we're solving for, is torque over I. We need to find I, the moment of inertia. I then is the moment of inertia of the first child, plus the moment of inertia of the second child, plus the moment of inertia of the seesaw itself. So for the first child, we have m1r1 squared. For the second child, we have m2r2 squared. For the seesaw, you can look that up in the table, and it approximates a rod or a board that's being rotated about its center. So a seesaw would probably be more, if you're looking at the table in your book, a flat plate about a central axis. 1/12 ma squared is as the book gives it. So we plug in all these numbers, and we get a moment of inertia totally of 240.8 kilograms meters squared. From there, we can solve for alpha. Alpha is torque over moment of inertia. And again, I've dropped the negative on torque. And so we get 0.35 radians per second squared. For number 80, I'm going to show how to do this using torques, and then I'll show an alternate solution that you can use center of mass to solve it. So, number 80, mechanical equilibrium. A meter stick is initially balanced on a fulcrum. 4 identical masses. Where should the 4th mass be placed to balance the meter stick? So you see the diagram I've drawn. The first mass is, now we don't just write down where the masses are located on the meter stick. What's important is how far it is from the fulcrum. So the first mass that's at the 25 centimeter mark, that is 25 centimeters away from the fulcrum. The second mass, because the fulcrum is at the 50 centimeter mark, the second mass is 5 centimeters away. The third mass is 45 centimeters away on the other side, and we want to know where the mystery mass is. And we don't yet know whether it's going to be on the left or on the right. I've just put an M here with a question mark. We need to figure out where it is. Here's what I'm going to do. I'm going to guess that it's on the right side of the fulcrum. If I'm wrong about that guess, that will become apparent in the solution. So let's just guess it's going to be somewhere around here. And we're going to figure out how far to the right of the fulcrum it's going to be. So if this thing is balanced, this is what mechanical equilibrium means. The sum of the torques equals 0. All the torques balance out. So torque for every individual mass is going to be its weight, the force it's pushing down, times its lever arm. So for the first one, that's its weight, G times M times 25 centimeters, plus for the second one, M times G, its weight, times 5 centimeters. The ones on the right are pushing in a clockwise direction, so we're subtracting them. So minus, and here's the mystery mass, M times G times how far to the right of the fulcrum, and I'll call that X, minus M times G times 45 centimeters, and to be in equilibrium, those all should add up to 0. M and G factor out and divide out of the equation, so now we have 25 centimeters plus 5 centimeters minus X minus 45 centimeters equals 0. And when we solve for that, we get X equals negative 15 centimeters. So I defined X as how far to the right of the fulcrum. It's coming out in negative numbers. That means it's 15 centimeters to the left of the fulcrum, or it'll be on the 35 centimeter mark. Now we could have also done this problem if we had guessed that the mystery mass would be on the left. We should be coming out with an answer of positive 15 centimeters. Let me show an alternate solution to number 80. You can do this using concepts learned in an earlier chapter when we studied center of mass. So here it is. The masses and the mystery mass, we don't know where it is in the fulcrum. Use the center of mass equation, where we know the center of mass is at 50 centimeters. So 50 centimeters equals M times 25. Remember, center mass equation is M times each position. And I'm designating the positions, I'm designating the x-axis as being aligned with the numbers on the meter stick. So 0, at the 0 mark, that is 0. That's the origin. The 100 mark is going to be x equals 100. So 50 centimeters, which is the center of mass, equals M times 25 plus M times 45 plus M times x plus M times 95. We don't have to guess whether it's going to be on the left or the right of the fulcrum. X is just going to tell us what centimeter mark it's going to be at, divided by the sum of the masses, which is 4m. The m's factor out in the numerator and divide out. We're left with 50 centimeters equals 25 plus 45 plus x plus 95 divided by 4. And we get x equals 35 centimeters. I'm going to do number 81 similarly to how I did number 80. I'll solve it using concepts of rotational dynamics and torque, and then I'll show an alternate solution using concepts of center of mass. So number 81, meter stick of negligible mass. Okay, we have one mass at 35 centimeter mark, the other at the 75 centimeter mark. Now, we set this up, again, if it's just like in number 80, if it's going to be in mechanical equilibrium, if it's going to be in mechanical equilibrium, then the sum of the torques equals 0. We need to come up with values that we can plug in for the lever arms. If you look at the diagram, let's call r the distance from the first mass to the fulcrum. That's what we're going to solve for. Since 35 centimeters and 75 centimeters is a distance of 40 centimeters, then the distance from the second mass to the fulcrum is the 40 minus r. If this is r, this has to be 40 minus r. So those are the two lever arms. Now we apply this into the sum of the torques equation. Sum of the torques is, each torque is force times lever arm. I've left something off here. Let me add this. Torque is really force times r. The force is the weight, which is m times g. M times g, m times g. But the g's are going to factor out and disappear. They're going to divide out. So after writing them, I can just cross them out. And we're left with 0.20 r minus 0.40 times 40 minus r equals 0. Little bit of regrouping, and we get these lines of algebra. Let's take it down here. 0.60 r equals 16. So we get r equals 26.6 centimeters. Now, that's 26.6 beyond the 35 centimeter mark. So 35 plus 26.6 is 61.6 centimeters. That's where we're going to have the fulcrum, so this balances. Let me show an alternate solution using center of mass. X center of mass, it's actually much easier to do it this way, is the sum of each mass times its position. So 0.2 kilograms times 35 centimeters plus 0.4 kilograms times 75 centimeters over the sum of the masses, 0.6 kilograms. And when you solve that, you get 61.6 centimeters. So once again, we find that it will balance at the 61.6 centimeter mark.